let me make the following parameterization, which is very important, because whenever we have n-body systems, okay, it is useful to define two types of couplings, okay? So one is the coupling simply alpha, but there is another coupling, as we will see, it will emerge automatically, n times alpha, okay? So somehow n times alpha is a collective coupling, which tells you how important the collective effects could be, okay? This is widely used, for example, in condensed matter physics and stuff. This type of coupling happens all the time. Even in gauge theory, this is called Toft coupling, okay? In large color QCD and so on. Now, this will emerge, as we will see, okay, from here. So therefore, let me do the following thing. I want to understand where is the critical end for which something will happen, and these gravitons of wavelength L can form a bound state, okay? What should I do? I should scatter them, okay? What I do scattering of gravitons. So I have an n-graviton system, and what is the situation? The situation is that in the first approximation, because I'm in the weak coupling regime, tremendously weak coupling regime, I will look for the effect on individual gravitons coming from the rest, okay? So I have one graviton, and that is n minus 1, and this n minus 1 is acting on this 1, okay? So in other words, I'm looking from the point of each graviton, the scattering between 1 and n minus 1, okay? And see when the scattering becomes important, so that it can potentially form a bound state. So what do I have to do? I have to do the following thing, right? I have to do this type of scattering amplitude, okay, between 1 and n minus 1 or n, because since we are in large n, okay, this difference doesn't matter for a moment, okay, so between n and n. Okay, so I have to compute this scattering amplitude, okay. Now, as we discussed in the previous lecture, okay, we can compute, and now we will see where quantum mechanics enters, where is the classical part. The classical part that will survive as a limit when I take classical limit of the theory, and what is new coming from quantum mechanics, okay? Where is quantum mechanics? Now, what is this amplitude? This S-matrix element for this thing will be the following expression, right? So will be, okay, there is an interaction between these gravitons, right? So will be, okay, dx, let's say dx1, dx2 integral, okay? Two vertex interaction. T mu nu at some point x, 1, then the graviton propagator, and T alpha beta at point 1 and 2, okay? Where? Okay, let me lift this up. Where the this is the graviton propagator that we derived in the previous lecture. Let me just remind you that this is simply 1 over box acting on the following tensorial structure. Will be symmetrized, mu alpha, mu beta symmetrized. I have chosen the same gauge, the Donder gauge, okay, for this. So this is the graviton propagator, which, okay, this is 1 over box, right? Or you can, I don't know, let me write it here. Or of course you can rewrite it in the Fourier transform form, the square with the same tensorial structure, okay? Now, okay, G Newton, I can write either here or there. Okay, I can write it there. So there must be G Newton, sorry. The because each vertex is square root from G Newton, so therefore will be 1 G Newton here, okay? Okay, so now, so where is quantum mechanics there, right? So we showed that the, right, in this diagram, where is quantum mechanics? Where is quantum mechanics in this expression? Now, quantum mechanics is not in this virtual graviton exchange. This virtual graviton exchange would perfectly nicely give you what would be the classical force, okay, between any source with the energy momentum T mu nu and T mu nu, okay? This would simply give you that. So the quantum mechanics here is in T mu nus, okay? The fact that now T mu nu, okay, these T mu nus are normal ordered products of the creation and annihilation operators, okay? So this is very important because this is bilinear in H, okay? So therefore, T mu nu, quantum mechanically, okay, what is important? Important is that each T mu nu will give you factors of, so T mu nu is bilinear in H square, okay, right? So this gives you factor of H, right? Because remember, since this is bilinear in H, this is bilinear in H, and classically H is square root from H bar times quantum, which in something quantum that involves creation and annihilation operators, okay? Now this H bar, H heads, these are just normal creation and annihilation operators with some tensorial structure, okay, with some helicities. You have to separate helicities accurately and so on. But this is not important for this quantumness discussion. Quantumness discussion is important is this. And the fact that these guys are normal order products of some creation and annihilation operators, which means that they have the structure of the form A dagger A. Of course, you will have this summation over momenta and helicity tensors, and so on, okay? This is the entourage that always is there. So that's where the quantum mechanics enters. So this means that quantum mechanics enters in these two H bars that appear in these two vertices, okay? Now, where else the quantum mechanics enters? The quantum mechanics enters in the quantum state in which you have to take in and out quantum state in which you have to take this matrix element. Okay? This n here, right? So your in state is some n graviton state plus 1 graviton, and then out state is some n graviton state plus 1 graviton. There is some transition. Of course, this transition is scattering, so the initial and final momentum will not be equal, and so on. Okay, the usual scattering. Okay, so now let's see what this diagram will give us. Actually, it's very easy because of the following reason, right? What do we have? We will have one H bar from here, okay? Right? Now, remember that we are simplifying our life because we are considering n graviton story with characteristic wavelength L, okay? So all the momenta are of the order H over L. Okay? So therefore, once I convolute, I'm looking for the initial states of this type. Once I convolute the matrix element that integrates over, characteristic momentum that will appear is this. Okay? So what do we get? We get the following structure, right? So now watch that so the propagator. Okay, so T mu nu will give me the following factor, right? Each T mu nu will give me H bar. Then creation annihilation operators ordered. I have the normal order, right? There will be two destruction and two creation operators, okay, some structure like this. And I have to convolute between initial and final states, okay? So I destroy one graviton, create